Good morning, dear students. My name is Ferhan Mazher, and the subject we are studying today is O Levels Physics 5054. Today, we have set our hearts to solve paper 4. We call it ATP, Alternative to Practical. For this purpose, we have selected October-November 2011 a 4-1 paper. This paper 4, this ATP paper belongs from the zone 1 or the variant 1. My name is Farhan Mal. So let's start today's paper. So here we go. So on your screen, the paper showing up is University of the Cambridge International Examination, General Certificate of this ordinary level, education ordinary level. Okay, so we have October, November 2011 4-1 paper. We call it paper 4. The time allowed is 1 hour. Total marks are 30. So it says a long pendulum is attached to the ceiling as shown in the figure 1.1. So here we have a ceiling with this, we have this string, and at the end of the string, we have a bob. A student performs an experiment to investigate the relationship between the time for one complete swing of the pendulum bob and its height above the floor. Height above the floor means the height above the floor. So they're talking about this height. Okay, so we are going to investigate the relationship between the time period of the pendulum and the height of the pendulum above the floor. So they are talking about this height. The vertical distance h of the bottom of the pendulum bob above the floor is measured, marked, and labeled on the figure 1.1. So we have to mark this height. The vertical distance h, so you have to draw a line here that is represents the height of the bob above the floor. So I will draw a line here, and then I will draw a line here and put arrows like this, and I will label it as h. The position of the eye of the observer when measuring h. So you have to position your eye exactly here. Okay. So the eye of the observer should be here. It should be perpendicular to the level of the bob. So let me show you my solution. You can see here. Okay, so you can see I have drawn that. So this is that height, and I will label it as h, and this is the eye of the observer. This is exactly at the level of the bottom of the bob. So this is what they have asked you to do. Okay, now they're saying that the pendulum is made to swing freely, and a stopwatch is used to determine the time for 5 swings, for 5 complete swings. T5 means time for 5 swings. The student takes a series of reading of 5 T5 for different values of H. Value of the H and the T5 are recorded in the figure 1.2. So they are basically measuring the time for, they are measuring the time for the 5 swings, and when the H is 5, when the H is 15, and when the H is 25, when the H is 35, when H is 45, when H is 55. So these are the times, and here this capital T means the time for one swing, and we can measure that, we can calculate that. Another student states that the measuring the time for 50 complete swings is better. But first of all, we have to complete this. Okay. So this is the time for 5 swings. This is the time for the 5 swings. So what you will do, you will divide it with the 5. You will get the value of t. Then you will square the value of the t. Same way, divide this with the 5. You will get the time for one swing, and then you will square it. You will write the square value here. Divide 14.59 with the 5, and whatever the value you get, you put it here, and then you square it. You put that value here. 14.23, you divide it with the 5, you get the value for one swing, and then you square it. 13.87, you find the value and you divide it with the 5, and that gives you the time period for the one swing, and you square it, you write it here. 13.49, you divide it with the 5, and that gets you the time for one swing, and then you square it, you write that value here. So let me show you, and this is the table. So you can see I have done this table. You can also do this. So, my dear students, you can see that this is the marking scheme for the question number 1A part and the B part. So you can match your answers here. I've already checked my answers and they are good. So, so we are going to the next question. The next part, he says, another student states that measuring the time for 50 complete swings is better. Suggest one disadvantage of timing 50 complete swings. You see, 5 swings takes 15.3, 14.96 time. So if you try to find the time for the 50 swings, it will be a long time, and then the experiment will take a very long time. So, so the experiment will take longer. So that's why we'll not go for the to time the 50 swings. Another reason can be that in 15 swings, maybe the pendulum stops swinging. Okay, so you can write any answer. So let me show you my written answer here. 50 swings. So my answer coming is that the 50 swings take long time to complete. Okay, figure 1.2 also contains columns for the time t for one complete swing and for the t square. Complete the figure 1.2. We are done with that. Given the values of t square to three significant figures. Okay, so we have done that. Okay, so hopefully you understand. So that was okay. Now the next question is, it says on the figure 1.3, plot a graph of t square on the y-axis against h in the centimeters on the x-axis. Start your axis from for t square, we will start from the 7, and for h, we will start from 0. Draw the line of the best fit. Okay. So t square will be on the y-axis and the h will be on the x-axis. So this we have to start from the 7 and this we have to start from the 0. So let's look at the table first of all. So let me, where's that table? This is that table. So this is on the x-axis and this value is going from 5 to 55, and this t square will be on the x-axis and it will start from 7 and it is going up to 9.38. So according to that, we will make our grade. So let me show you. Okay. Okay, so this is the, so on the y-axis, I'm representing t square. You can see I have taken 2 centimeter represents 5.5. So this is 7.5, this is 8, and this is 8.5, this is 9, 9.5, and 10, 10.5. And on this axis, I have represented the h, and the h is represented in the centimeters. So 2 centimeter represents 10 centimeter. So you can see here where 10, 20, 30, 40, 50, and 60. And it's very important that you label it. This is called a labeling. That on the y-axis, I have represented the t square. The unit used is second square. On this, I am representing h, which is measured in centimeters. So then I will plot those points. You can see I plotted those points. And let me tell you at the, where are the points? So these are the points. At 5, you put dot of 9.38. At 15, you put a dot of 8.95. At 25, you put a dot of 8.51. At 35, you put a dot of 8.10. At 45, you put a dot of 7.7. And at 55, you put a dot of 7.28. So when you have plot those, put dots, these points, and then you join them with the line of the best fit. Okay. So you can see this point is on the upper side of the line. This point is on the lower side of the line. So this is the line of the best fit. By joining these points, you can do this. For the line of best fit, the one thing which I keep in my mind is that the number of points which are left above the line, they should be equal to the number of points left below the line. So this is the approximate line of the best fit, and that is a 4 marks question. Okay, so the next question they are asking is describe the shape of your graph. As you can see, this graph is going down with a constant gradient. It means that as you increase the value of the h, the value of the t square is decreasing. So we can say that they have, you will not use the word inversely proportional because this is not graph of inversely proportional. but they have an inverse relationship with each other. As the value of the h is increasing, the value of the t square is decreasing. So they have kind of inverse relation, but don't use the word inversely proportional because they are not inversely proportional. Neither this shape is graph of inversely proportional. So you can see here, I have written here, the graph is a straight line with the constant negative gradient. So as the h increases, the t square decreases. So they have inverse relation, but not the inversely proportional. Okay, so let me show you from here. So you can see for that graph what these are: one number, two number, three number, fourth number, and this is that the the fourth part of the question number one. So we are almost done with the question number one. So, okay, so now we are going to the next question. The next question is question number two. He says, let me reduce the size so you can see the whole question. He says a straw balance is used to measure the mass of a length of hair. Figure 2.1 shows a straw balance. Okay, so here you have a straw balance, and this needle is acting like a pivot. And this is paper straw. This end is flattened. This is a small screw here. This is the support. The straw is flattened. The straw is flattened at one end and has a small screw inserted into the other end. The needle is pushed through the straw to balance the straw on a support. When a mass is placed on the flattened end of the straw, that end moves down. The larger the mass, the more it moves down. The distance moved down is directly proportional to the mass. The height of the flattened end is adjusted by moving the screw into or out of the straw. State what happens to the flattened end when the screw is moved into the straw. If you will move this screw into the straw, the moment arm of this, the weight of this screw, that will decrease. So its moment arm or turning effect will decrease. When its turning effect will decrease, this will go down. Okay, because the balance will be disturbed when you move this small screw into the straw. The moment arm of the weight of this small screw decreases, due to which its moment decreases, turning effect decreases. So what happened? This goes down. This flattened screen will go down. Okay, so this is my answer. So let me show you my answer. Okay, where is that answer? Okay, place. Okay, sorry. Okay, flattened and goes down. Simple answer. So goes down. Okay, so this is the marking scheme. I hope you understand. Okay, so we are going to the next question, and here it says. So okay, now that is my answer. Okay, so we are going to the next question. He says, now he says the flattened end of the straw is placed in front of a vertical scale marked in centimeters, not with nothing on the flattened end. It points to 0 on the scale as shown in the figure 2.2. In order to use the straw balance to measure masses, the scale can be marked in grams. Explain how this is done. So what we will do, we will take some objects whose mass we already know. For example, you take an object whose mass is 1 gram and you know already that its mass is 1 gram. You take an object whose mass is 2 gram. You take a mass, the object whose mass you already know. Okay? So you will place that object here on the flat end, and obviously this will go down. So for example, I put here a mass of 1 gram. So this, what will happen? This straw will go down, and wherever it stops on the scale, put a mark, and with it write 1 gram. Then take that off and put a mass whose mass is 2 grams, and put this on this flat end, and it will obviously go down. So wherever it stops on the scale, put a mark and write there 2 grams. So in this way, by putting a known mass on the flat end, on this right end of this straw, wherever the straw stops, on the scale you put a mark and there you write the mass of that object. So in this way, by putting the known masses on the straw, you can calibrate this scale to find the mass. So this is my answer. So let's see what my answer has to say. It says, okay, so this is my answer. Place known masses and mark the position of the flattened end on scale. Write mass on scale on each position of the flattened end. Okay, so whatever is the known mass you have put there, whatever is the position of the flattened end, just put a mark on the scale and write its mass there. So this is how you write it. Okay, so uh, use a known mass stated or employed with link to centimeter marks on the scale. Okay, so this is how you do it. This is the marking scheme of question number 2. Then he says, the student places a 2 millimeter square of paper, graph paper, on the flattened end and of the straw. The end of the straw goes down as shown in the figure 2.3. So it has gone down 1 point, I think, this is 1.12, 1.25. So state the reading on the scale. So if you want to find out the reading on the scale, so let me increase the size so you can see it more clearly. So, so where is this? This is 1, this is 1.2, 1.4, 1.6. So this will be 1.5. So the exact reading is 1.5. Okay. So the reading is 1.5. Let me show you. So the reading will be 1.5 centimeters. So 1.5 centimeters. So our answer is right. Okay. So now, then he says the graph paper is removed and the length of a hair is placed on the end of the straw as shown in the figure 2.4. And he says state the new reading on the scale. Okay, so I will increase the size to see it clearly. So let me show you. So what is this reading? This is 3.2, 3.4, 3.6, 3.8. So the reading will be 3.8. So the reading is 3.8. So I will write here 3.8. So I will write here 3.8. As you can see, I have written here. So let's check from here. 3.8 is the right answer. Okay, then they say, so just one advantage of a straw balance when compared with an electronic digital balance. You see, in the electronic digital balance, you need the electricity. For that purpose, we use cells. And in the straw balance, you don't need electricity. So you don't need the cells. You don't have to change the cells. So that is the advantage of using the straw balance. So my answer is, a student, one advantage of straw balance when compared that it does not need electricity to use. Okay, so I think we have left one question. I think one question has been left by me. The student, see, the student is told by a teacher that the piece of graph paper has a mass of 0.30 milligram. To calculate the mass of the hair. So I can calculate the mass of the hair. I know in both cases, I know the length of the straw which it has gone down. So when the length is 1.5 centimeter, the mass is 0.30 milligram. And when the length is 3.8 centimeter, how much is the mass? I'm going to use the method of proportion. So it will be 0.30 divided by the x equals to 1.5 divided by 3.8. So when the straw moved down 1.5 centimeter, it was 0.30 milligram mass. And if the straw has moved 3.8 centimeter, how much is the mass? So just cross multiply 0.30 divided by x is equals to 1.5 divided by 3.8. So the x will be equals to 0.30 into 3.8 divided by 1.5. So it will give you 0.76 milligrams. So it will give you 0.76 milligram, and that is right answer. By chance I missed this part. Now I have made it clear. So this is the proportion method which I have used. Okay, so I think, okay, then the question is, okay, we have the next question. Here we have a question. He says the cathode ray oscilloscope CRO is used to check the voltage of a cell. Figure 3.1 shows the cell in a simple circuit and also the front of the CRO. Okay. So what they want is, this is the CRO, the Y gain is set at the point, it is at 2 centimeter, 2 volt per centimeter. The time base is on, this is X shift, Y shift, and these are the inputs. Okay. So what they say, the CRO is switched on and the time base is switched off. A bright dot is seen on the screen as shown in the figure 3.1 state, which controls are used to move the dot to the center of the screen. Okay, so the dot right now is not in the center of the screen. So with the help of the Y shift, I can move the dot up and down. With the help of the X shift, I can move the dot right and left. So by using these X shift and Y shift, I can bring the dot in the center of the screen. So this is my answer. So let's see. Y shift is used to move the dot up and down. X shift is used to move the dot to the right or to the left. So you can move the dot up and down, right and left, and it can be brought to the center of the screen. On the figure 3.1, it says on the figure as a state watch control. Okay. On the figure 3.1, draws connections from the circuit to the CRO. Draw connections from the circuit to the CRO so that the voltage of the cell can be measured. Okay. So from here, I will take one wire from here and I will put it here, and one wire from here and I will put it here. So you put the connections into the Y input and the display of that voltage will be shown on the CRO. So let me show you, we have to draw this. Okay, so here you can see I have done the connection from these two ends with the Y input. So if you want the shape of that the voltage to be made on that CRO screen, so you will connect the leads with the Y input. Okay. Okay, Y shift and X shift connections from either side of the cell resistor to the Y inputs. Okay, so answers are right. Okay, so the next part. He says the dot is now in the center of the screen. Figure 3.2 shows the dot on the screen of the CRO before and after the cell is connected. So when you have connected the cell, the dot has gone upward. Using the figure 3.1 to state what is represented by the 1 centimeter on the vertical axis on the CRO. Okay. So from this setting, you can see that the Y gain is set on the 2, which means that 1 centimeter represents 2 volt. The Y gain is set on 2 volt per centimeter, which means in 1 centimeter, we have represented 2 volts. Then the question is determine the voltage of the cell. So if you put a scale here, you will find from mean position, it has gone up 0.8 centimeter. So 1 centimeter basically represents 2 volts. So 0.8 multiplied 2, and that will be 1.6 volt. So 2 volt and 1.4 to 1.6 volts. So our answer is right. Then he says, describe and explain what is observed when the connection from the circuit to the CRO are reversed. If you will reverse the connections with the CRO, these connections, I want to say these connections. If you reverse them, this graph, instead of going upward, 0.8 centimeter, it will go 0.8 centimeter downward. The dot will be 0.8 centimeter below its mean position on the screen, because when you will connection to the circuit, when you will reverse them, the graph from the mean position. Instead of going up 0.8 centimeter, it will go below the point, below that point, the mean position, 0.8 centimeter below the mean position. He says the time base is switched on. When you will switch on the time base, that dot will become a horizontal line, and that horizontal line will be 0.8 centimeter above the central position of the screen. The center of the screen, it will be a horizontal line then when you switch on the time base. So this is that answer, question number 3. I hope you understand. A student investigates the refraction of the light through a parallel-sided glass block. The figure 4.1 shows the student's diagram. The line represents any array of light arriving at the upper surface of the block. The student forgets to mark the lower surface of the block. The student draws two crosses, M1 and M2, in the path of the emergent ray. So on the figure 4.1, draw normal through the point where the ray enters the block. So here you have to draw this normal at this point where the light has entered into the glass block. So this is that normal. With the help of the protector, I will draw this line. This line makes 90-degree angle with the surface of the glass. Then it says mark the angle of incidence and label it I, measure the angle of incidence I. So I will mark this angle between the incident ray and the normal as I, and then I will measure it. So when I will measure it, this will be 30 degree. It will be how much? 30 degree. The distance between the upper surface and the lower surface of the block is 5 centimeters on the figure 4.1. Draw the lower surface of the block. Okay. So let me show you how this is done. Because you will remain parallel, the lower surface will be aligned parallel to this line. So, and that should be at a distance of 5 centimeters. So what I will do on this vertex, I will draw a circle of 5 centimeter. On this vertex, I will draw a circle of 5 centimeter. And I will draw a tangent here. And that tangent will represent the lower boundary of that glass block. Okay. Complete the path of the emergent ray from the lower surface of the block through the M1 and M2. Okay. So I will join M1 and M2 with each other until you reach the block. Once I'm here, I will join this point of incidence and this point of emergence with each other. Okay. Complete the path of ray within the block. Okay, so we are done with that thing. Measure the angle of refraction R inside the block. So inside the block, this is the angle of refraction. I can put a scale here and I will measure how much is this angle. Okay. That will be 18 degree. The angle of refraction will be 18 degree. If I will measure this angle, I put the cross of your D here, protector here, and here I will put the 0 and I will check how much is this angle. That is the angle of refraction. That will be 18 degrees. So let me reduce the size so I can see what is this. Okay. So we are done with this paper. Okay. So this is that diagram. And this is the marking scheme. So I think our answers are right. So we are done with this paper today, my dear students. Today we have done October, November 2011 Physics 505441 alternative to practical paper. And this solution of the past papers And I hope that you have understood this paper. I hope that you have understood the concepts. If you have understood, you have learned from this video. Please share the link of this video onto your Facebook, onto your Instagram, and onto your Twitter accounts. Also, like this video. Also, tell students around you, about your junior students, senior students, about this video, because that will help me promote my channel. Thank you very much, sir. It's a great blessing for me to make these videos and to touch so many lives around the globe. Thank you very much. Have a good day. God bless you all.